the constant volume gas thermometer, and In this session, we will explore several key topics related to temperature measurement and thermal properties. We will begin by comparing liquid thermometers and identifying their inherent limitations. This leads us to the mechanism of the constant volume gas thermometer, which provides a more consistent standard for measurement. We will define the absolute temperature scale and discuss how to perform temperature scale conversions between Celsius, Kelvin, and Fahrenheit. Finally, we will cover the basics of thermal expansion, examining how substances change in size when their temperature increases. While liquid thermometers are common, they have significant limits. When we calibrate different thermometers, such as those using mercury or alcohol, at the ice point of 0 degrees Celsius and the steam point of 100 degrees Celsius, they might still disagree at temperatures in between. These discrepancies occur because different materials have different thermal expansion properties. Furthermore, their practical range is restricted by the physical properties of the liquids themselves. For example, mercury becomes a solid at -39 degrees Celsius, and alcohol begins to boil at 85 degrees Celsius, making them useless beyond those points. The images show a mercury thermometer rising as it is heated, illustrating the basic principle of expansion. To overcome the limitations of liquids, we use the constant volume gas thermometer. This device exploits the fact that the pressure of a fixed volume of gas varies with temperature. As shown in the diagram, a gas-filled flask is immersed in the environment to be measured. To keep the volume constant, we adjust the height of a mercury reservoir, labeled B, until the mercury level in column A returns to the 0 mark on the scale. We then calculate the gas pressure by adding the atmospheric pressure to the product of the density of mercury, the acceleration due to gravity, and the difference in height between the two columns. Calibration of the gas thermometer involves measuring the gas pressure at two known reference points: the ice point at 0 degrees Celsius and the steam point at 100 degrees Celsius. These two data points are plotted on a graph of pressure versus temperature. By connecting these points with a straight line, we create a calibration curve. Extensive experiments have shown that gases exhibit a very linear relationship between pressure and temperature, meaning that once this line is established, we can determine any unknown temperature simply by measuring the corresponding pressure of the gas. A fascinating property of gas thermometers is that their readings become nearly independent of the specific gas used as long as the pressure is kept low. If we take the pressure-temperature graphs for different gases and extrapolate the lines down to 0 pressure, we find a remarkable result. Regardless of the gas type, every line intersects the temperature axis at exactly -273.15 degrees Celsius. This temperature is defined as absolute zero. Since pressure cannot be negative, this point represents a natural lower limit for temperature, serving as the foundation for the absolute scale. The Kelvin scale is the SI unit for absolute temperature, with the unit being the Kelvin. Unlike other scales, it uses two fixed points that do not depend on atmospheric pressure: absolute zero and the triple point of water. The triple point is the unique temperature and pressure where water exists simultaneously as a liquid, a gas, and ice. This occurs at 0.01 degrees Celsius and a pressure of 4.58 millimeters of mercury. For this scale, the triple point is set at 273.16 kelvins. Crucially, the size of 1 Kelvin is exactly equal to the size of 1 Celsius degree. We can convert between the three major temperature scales using specific mathematical relationships. To find the Celsius temperature from a Kelvin value, you subtract 273.15. To convert from Celsius to Fahrenheit, you multiply the Celsius temperature by 9/5 and then add 32. When looking at temperature changes, a change of 1 degree Celsius is exactly equal to a change of 1 Kelvin, and both are equal to 5/9 of a change in degrees Fahrenheit. It is a vital rule in physics to use the Kelvin scale for any equation that involves ratios of temperatures. Absolute temperatures in nature span a vast range, which is why we often use a logarithmic scale to visualize them. At the highest end, the interior of a hydrogen bomb or the center of the sun reaches about 10 million kelvins. The surface of the sun is much cooler, at approximately 6,000 kelvins. On the lower end, liquid nitrogen exists at 77 kelvins, while liquid helium is near 4 kelvins. While the absolute zero of 0 kelvins can never be reached, scientists have achieved temperatures lower than 1/1000th of a Kelvin in laboratory experiments. Let us look at a practical conversion example. If the temperature outside is 50 degrees Fahrenheit, we can find its equivalent in other scales. First, we convert to Celsius by subtracting 32 from 50 and multiplying the result by 5/9, which gives us exactly 10 degrees Celsius. To find the temperature in kelvins, we take that Celsius value of 10 and add 273.15, resulting in 283.15 kelvins. Remembering that 10 degrees Celsius is a cool day helps provide context for these numerical values. Now we turn to thermal expansion. Generally, as the temperature of a substance increases, its volume also increases. This happens because higher temperatures cause atoms to oscillate with greater amplitudes, which increases the average separation between them. We can quantify this using the average coefficient of linear expansion, represented by the Greek letter alpha. This coefficient is defined as the fractional change in length divided by the change in temperature. In simpler terms, the change in length is proportional to the initial length and the total change in temperature. Thermal expansion has critical engineering applications. Engineers must include expansion joints in bridges, highways, and buildings. These joints, like the interlocking metal teeth shown in the bridge photo, allow sections to expand or contract as weather changes, without causing the structure to buckle or crack. Similarly, vertical joints in brick walls are filled with soft material to accommodate these shifts. You might also notice that power lines sag more on hot days. This is because the wire expands in length between the fixed poles as the temperature rises. To summarize our key points, gas thermometers provide a universal scale that does not depend on the specific material used. Absolute zero is defined as negative 273.15 degrees Celsius, the point where gas pressure would theoretically reach zero. The Kelvin scale is the standard SI unit starting from this 0 point. While temperature differences are the same in Celsius and Kelvin, they differ in Fahrenheit. Finally, we learned that thermal expansion is a physical consequence of atoms moving further apart as they vibrate more intensely at higher temperatures. We conclude with 2 review questions to test your understanding. First, consider why the agreement between different gas thermometers improves as the pressure of the gas used in the thermometer is reduced. Think about how gas behavior approaches an ideal state at low pressures. Second, if an object's temperature increases by 20 kelvins, what is the corresponding temperature increase in degrees Fahrenheit? Remember to use the relationship for temperature changes rather than the formula for specific points on the scale.